Since its launch, the James Webb Space Telescope has made some fascinating discoveries about the early universe. One of the most intriguing findings comes from its observations of mature, primordial galaxies. These galaxies appear far too massive, too evolved, and too structurally mature for the time periods in which they existed. Their presence challenges our very understanding of how the universe evolved. But what if this strange behavior isn't just a flaw in our models, but a matter of perspective? What if the Webb telescope has been pointing us toward an entirely new view of reality? The key to this puzzle lies in redshift, the stretching of light as the universe expands. The further away a galaxy is, the more its light is redshifted, allowing astronomers to measure its distance and age. JWST has been pushing this to the extreme, peering back over 13.5 billion years into the universe's 13.8 billion year history. The standard model predicts that galaxies at this stage should be small and irregular. Instead, Webb has found massive, well-formed galaxies with significant structure, and their presence have led scientists to rethink our understanding of the universe. But what's more fascinating is that the latest JWST Advanced Deep Extragalactic Survey observations of 263 galaxies reveal a strangely coordinated cosmic motion. It suggests that our universe might be inside a black hole. Welcome to territory. This is your space. A new research analyzing JWST observations of the early universe has uncovered an intriguing mystery. The majority of galaxies appear to be rotating in the same direction. The lines formed by the peaks here allow us to identify the direction of the curve of the arms of the galaxies, and consequently, their spin direction. This is significant because in a truly random universe, galaxy rotations should be roughly evenly split between two directions. According to the study's authors, this unexpected finding, which contradicts existing cosmological models, may hint that our universe itself is inside a black hole. To understand this, we need to look at the physics of black holes. When matter collapses under gravity to form a black hole, it creates an event horizon, a boundary beyond which nothing can escape, not even light. Anything that crosses this boundary is forever lost to an outside observer. However, what happens inside the event horizon is still a mystery. This is where black hole cosmology comes in. Also known as Schwarzschild cosmology, it suggests that our observable universe might actually be the interior of a black hole within a larger parent universe. This brings us to the Big Bang. The standard model tells us that the universe began as a singularity, a point of infinite density, just like the center of a black hole. If our universe is actually the interior of a black hole that formed in a larger parent universe, it would mean that the Big Bang was not an expansion into empty space, but rather the moment matter collapsed into a black hole, creating a new universe inside. This would mean that every black hole in our universe could be the gateway to an entirely new universe. This could also explain why the fundamental constants of our universe appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and give rise to new ones through this process. The scientists believe that this idea could explain several cosmic mysteries. For example, black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. Another factor that could play a role in this scenario is torsion. In extended theories of general relativity, such as Einstein-Cartan relativity, torsion is a property that accounts for the intrinsic spin of particles and can influence space-time curvature. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. In that scenario, instead of collapsing into an infinitely small point, a black hole could experience a big bounce, where the core rebounds and expands outward, potentially giving rise to a new universe inside. The scientist added that a rapid recoil after such a big bounce could have initiated the expansion of our universe, an event we refer to as the Big Bang. Hence, instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. This theory would drastically change our understanding of cosmic origins, suggesting that the cycle of universes is an ongoing and self-replicating process. Another intriguing possibility is that the universe may have a preferred axis. Observations of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. Also, the existence of massive primordial galaxies challenges our understanding of cosmic evolution. But we need to also consider that while the universe inside a black hole theory is tantalizing, there could also be a more pedestrian explanation for the unexpected observations. Maybe some earlier measurements of our universe are incorrect, especially the speed at which the Milky Way galaxy rotates. Maybe the universe is older than we think it is. In any case, the universe is turning out to be far stranger than we once imagined, and the uneven galactic rotations will likely prompt astrophysicists to reassess certain aspects of our understanding of the universe. What do you think? Is our universe inside a black hole? While this is a fascinating theory, there's another research paper that came out recently that proposes the universe has a twin, a mirror universe where time runs backwards. For those who have watched it already, you can skip it, but those who haven't, please give it a watch.
Haven't you ever heard of Occam's razor? The simplest explanation is probably the correct one.
In the world of scientific reasoning, there's an effective principle known as Occam's razor. Suppose astronomers observe unexplained lights on another planet. Instead of concluding aliens are there, Occam's razor asks them to consider simpler causes first, like atmospheric conditions or natural planetary phenomena. But why bring up Occam's factor here? Well, many inflation models suggest that the rapid expansion of the early universe should have created long wavelength gravitational waves, basically ripples in space-time. Detecting these waves would provide strong confirmation of inflation. Now, to be clear, scientists have detected gravitational waves, but coming from events like merging black holes and neutron stars. And despite many sensitive searches, no signs of these primordial waves have been found, with each new experiment ruling out more inflation models. While the inflation theory does explain some issues, like why the universe looks so uniform on a large scale, it also introduces new challenges like, what energy field actually powered inflation? Inflation requires the universe to have very specific initial conditions, but why were these conditions present to begin with? Some inflation models suggest infinite bubble universes. This raises philosophical and scientific questions about testability and the nature of physical reality. So ignoring the Occam factor here would be basically assuming that there are no simpler explanations. That is something Neil Turok, the Higgs Chair of Theoretical Physics, set out to change. Together with his colleague Latham Boyle, Turok approached a new theoretical model that could address fundamental cosmic questions without relying on traditional inflation and string theory. If we use Einstein's theory of general relativity and the known laws of physics to follow the universe backward in time, we arrive at a point where space and time shrink to a single point called the initial singularity. To make sense of the extremely dense, hot state at the beginning of the universe, theorists like Nobel laureate Roger Penrose identified a key symmetry in the laws of light and massless particles. This symmetry, called conformal symmetry, suggests that neither light nor massless particles experience the usual shrinking of space at the Big Bang, allowing them to bypass the intense conditions that otherwise affect all other forms of matter. Imagine you have a stretchy rubber sheet, like a rubber band, with a drawing on it. Now, if you pull or squish that rubber sheet, you might change the size of the drawing, but you're not changing the shape of the things in the drawing. Conformal symmetry implies that the universe could have a similar structure, remaining unchanged no matter how you scale it. This property could mean that rather than being shaped by an explosive event like inflation, the universe's evenness might arise naturally from this symmetry. They proposed that the initial singularity, instead of being a one-way origin, acts like a mirror in time. On one side, time flows forward. On the other, it flows backward, like a cosmic reflection. This mirror at the Big Bang aligns with the idea that every physical process has a mirror counterpart, where space, time, and particles are reversed, thus following CPT symmetry, a fundamental balance in nature. Imagine the universe as a grand stage where particles act out a play. In this play, three special rules, charge, parity, and time, govern how things behave. Charge is like swapping matter for antimatter. Parity flips the scene as if you're looking in a mirror, and time is running the play backward. Now, if you change all three at once, flip charges, mirror everything, and run time backward, the laws of physics stay perfectly unchanged. The universe doesn't break a sweat. It still plays by the same rules, like a well-rehearsed performance, no matter how you rearrange it. Yet the apparent dominance of particles over antiparticles and the unidirectional flow of time in our universe make it seem that CPT symmetry might be violated. The mirror universe concept, however, reinstates this symmetry by suggesting that our universe has a reversed mirror counterpart. In this mirror reality, time moves backward and antiparticles outnumber particles. This parallel universe need not be a real place, but could be a mathematical construct to explain symmetry at the universe's origin. Their theory also sheds light on dark matter. Neutrinos, which are light particles moving near light speed, spin in a left-handed orientation. However, heavy right-handed neutrinos, predicted to be stable, are possible dark matter candidates as they interact only through gravity. Using their mirror hypothesis, Turok and Boyle calculated that these right-handed neutrinos could indeed account for dark matter. Basically, the theory suggests that if dark matter is made of heavy right-handed neutrinos, then out of the three types of known light neutrinos, at least one would have to have zero mass. This prediction is being tested by studying how galaxies and other cosmic structures are arranged in space. Observing how matter clumps together across the universe might reveal clues about neutrino mass, helping to confirm or refute this theory about dark matter. The scientists also tackled the mystery of why the universe appears flat and uniform on large scales. They explained this using the concept of entropy, which helps describe how likely certain configurations are. They discovered that a flat, rapidly expanding universe with a small positive acceleration is the most probable state. Additionally, they showed that density variations, usually linked to inflation, could actually be explained through quantum fields. However, more research is needed to ensure the new theory holds up scientifically. Picturing the Big Bang as a mirror neatly explains many features of the universe which might otherwise appear to conflict with the most basic laws of physics, wrote Turok, who published his team's findings in the journal Annals of Physics. The progress we have made convinces me that in all likelihood there are alternatives to the standard orthodoxy, which has become a straitjacket we need to break out of. While much more work is needed to support this fascinating idea, Turok suggests that even if proven wrong, it highlights the possibility of simpler explanations than those provided by the standard model. What do you guys think?